Hello and welcome to P2 Electricity. This lesson number 8, is on the national grid. My name is Mr. Cooper. I'm a Director of Science for Outlook Range Academies Trust, and I'm going to go through this lesson with you. So can you remove any distractions, turn off any mobile phones, and you'll need a pen and paper at the ready. Okay, for a starter activity then, we've got 4 questions. Question number 1, what is the voltage of UK main supply? Question 2, what is the frequency of UK main supply? Question 3, state the units of power. And question 4, can you state the units for current? And you've got 2 minutes to complete those 4 questions. Okay, then let's have a look at some of our answers then. So for the UK main supply electricity is anywhere between 230 and 240 volts. The frequency of UK main supply is 50 hertz. The unit of power is in watts, and the unit of current is in amps. So our outcomes for today's lesson, the Aspire outcome is to explain how and why transformers are involved with the national grid, and the challenge outcome is to identify and label parts of the national grid. Okay, so how does electricity reach our home? What you've got are 5 images there, and I'd just like to make some bullet points as to how you think electricity gets into our home. And I'll just give you 30 seconds just to make some notes. Okay, so for the next clip, what I'd like you to do is to answer these 7 questions. So, list how many ways we generate electricity. Number 2, what percentage of the world's electricity is generated through fossil fuels? Question 3, what turns the turbines in a power station? Question 4, what does the electricity pass through before it goes through the power lines? Question 5, how is energy lost in a wire? Question 6, what happens to the voltage when electricity comes from the power station? Question 7, what happens to the voltage before the electricity goes into our homes? Now you may be able to answer some of those questions already. If not, we're just going to watch the following clip and we'll be able to answer them at the end.
the flick of a switch. That's how easy it is to get electricity, right? If you're one of the lucky ones, then yes. But in 2017, there are still over 1 billion people who do not have access to electricity. In this video, we will discuss how electricity is generated and transferred to our homes, for those of us fortunate enough to have it. There are a variety of ways in which electricity is generated or made. How many can you think of? Some are shown in this image. Solar panels, wind turbines, biomass, hydroelectric, nuclear, and fossil fuels. And then there is also geothermal energy, tidal power, and wave power as well. Except for burning fossil fuels and nuclear, the rest are renewable sources of energy. Currently, about 80% of the world's energy comes from fossil fuels. First, we're going to have a look at burning fossil fuels in power stations to generate energy. And then we'll look at the national grid, which is relevant for both non-renewable and renewable energies. So fossil fuels in power stations. Most power stations use coal as an energy source, and they work in the following way. 1. Coal is burned in a power station. The heat produced as the coal burns is used to heat water. The water boils and turns into steam. 2. This steam is used to turn the blades of a turbine. A turbine looks like a fan or a wind turbine. The turbine turns a generator. Inside, wires turn within magnets to generate electricity. So that was a fossil fuel power station. These next steps are for energy generated from any source, whether it's fossil fuels or renewable, like wind-powered substations or biomass-fueled. 4. The electricity, whether renewable or not, is passed through transformers and wires within the national grid that carries it to our homes. So, what exactly is the national grid? The national grid is a system of cables and transformers linking power stations to consumers. Have you ever felt an electrical wire and noticed it gets hot? This is because some energy travelling through the wire is lost as heat. In order to lose as little energy as possible, transformers are used. When the electricity leaves the power station, it passes through a step-up transformer. A step-up transformer increases the voltage and reduces the current. Reducing the current makes the transfer of electricity more efficient, as less energy is lost as heat. Before the electricity gets to our homes, the voltage needs to be reduced back down to a safe level. The electricity therefore passes through a step-down transformer. To learn how transformers work, watch this video. So, now you know how electricity is generated and sent to our homes. It's not quite as simple as flicking a switch. Quite a lot of infrastructure is needed.
If you liked the video, give it a thumbs up and don't forget to subscribe. Comment below if you have any questions. Why not check out our FuseSchool app as well? Until next time.
Okay, so let's go through some of the answers that we've got. You've probably got a list of numerous ways of generating electricity, both renewable and non-renewable. Percentage of the world's electricity is generated through fossil fuels is 80%. What turns the turbines in a power station is the steam. What does the electricity pass through before it goes through the power lines? And that's transformers. Question 5, how is energy lost in a wire? Energy is lost through heat. And we've covered some of that when we looked at resistance. Question number 6, what happens to the voltage when the electricity comes from the power station? The voltage is increased. Question 7, what happens to the voltage before the electricity goes into our homes? Well, the voltage is then decreased down to 230 to 240 volts. So what I'd like you to do now is just to copy and label the diagram below. The national grid is a system of cables and transformers that link power stations to consumers. So I'll just give you a minute just to copy that diagram down. Okay, and within that diagram, it's actually these components that you'll need to know. These are the parts that you'll have to name in any kind of assessment or label in any kind of diagram. Power lines will accept the name of cables instead if needs be. Okay, let's take a closer look at transformers. So on the left-hand side in the red box, we've got a step-up transformer. We can see that 100 volts goes in and it gives you 400 volts out. 10 amps goes in and it gives you 2.5 amps coming out the other side. So the three questions: why do you think this transformer is called a step-up transformer? Question 2, what do you think a step-down transformer does? And question 3, how would a step-down transformer's structure differ? So I'll just give you a minute or so just to have a go at the questions 1, 2 and 3. Okay, so question 1, why do you think this transformer is a step-up transformer? As we can see, 100 volts goes in and 400 volts come out. So the voltage steps up, the voltage increases. Question 2, what do you think a step-down transformer does? Well, it would be an opposite to a step-up transformer. Therefore, a step-down transformer, the voltage would reduce. And the extension question, how would a step-down transformer structure differ? Well, if on the diagram you look at the green wire and you count how many turns or how many coils there would be in the primary component, there's 5 turns, and in the secondary coil there's 20 turns, and that's a step-up transformer. So in a step-down transformer, it would be the reverse. There would be more turns in the primary coil and there'd be less turns in the secondary coil. So if we look at both the step-up transformer and a step-down transformer, and we need to look more specifically at what happens to the current. So in a step-up transformer, we've got 10 amps going in, and it gives you 2.5 amps out. So you can see in a step-up transformer, whilst the voltage increases, the current actually reduces. And then if we look at a step-down transformer, as we've seen before, the opposite would happen. 2 amps going in gives you 10 amps coming out. So whilst the voltage reduces, the current increases. So they're all governed by the equation power, which is measured in watts, equals potential difference multiplied by current. Now, in order for power to stay the same, something needs to change either between the potential difference and the current. So at the step-up transformer, the power stays the same, but the potential difference increases. What therefore must happen to the current? Well, if the potential difference increases, therefore the current must reduce or decrease. A step-up transformer increases the potential difference across the transmission cables, which decreases the current. Now, if you increase the voltage and decrease the current, the power can stay the same. So, why do you think we need to step up the voltage to travel through the cables in the national grid? And there's the diagram that we must be able to label. You've got your step-up transformer, you've got your high voltage transmission lines, or cables, as we said we could call them, and we've got our step down transformer. The hint is it may need to consider the current and what the current does in a wire.
The national grid is a system that takes electricity from power stations to our homes. In this video we'll be looking at why we use transformers in this system. In this diagram you can see that the electricity comes from the power station and goes through a step-up transformer up to 132,000 volts or higher. Then it goes through a step-down transformer, reducing the voltage to about 230 volts for home use. I'm going to show you a demonstration that you can do in the classroom that shows the national grid.
So what you can see here is then our power station making some electricity. We're making 2.65 volts here, coming out here, and you can see that that's across our light bulb, so you can see the light there. What I've done is I've taken out the transformers here, so you can see what happens in our national grid if we didn't have any transformers. So here the electricity is coming up to our pylons here, across here, and you can see that already from 2.65 as it was, now only 1.4 volts, so it's gone down across here, across, down, and again I've taken out the transformer here, going down into this light bulb here. It's not even really lighting up, you can just about see that it's lit up, and then out of this meter we're down to 0.63 volts. So there's energy being lost all the way through the system till the end here, and if you imagine that was your home, you'd be paying for all of that energy that had been lost through all of the country, through all of the wires there, and that's obviously not a good thing. Obviously also would be wasting energy, would be wasting electricity, and we'd have to make that, maybe burn some more fossil fuels, so that wouldn't be a great thing either. Okay. So now this time we've got the transformers in, so again this is our power supply here, so this is like our power station. You can see again we've got 2.4 volts across our pole, and that's really bright. But now, here with our transformer, across these power lines now, you can see that we've got 36 volts. So with the transformer we've stepped up the voltage. That's a step-up transformer going across the power lines, and then back down. We're going through a step-down transformer, and this time you can see the bulb is actually bright. We have got a little bit of energy loss because now we're on 1.55, but it's a lot better than it was before. So the point of putting the transformers into our national grid is so that we don't lose as much energy across the whole of the national grid. So it's much more efficient, and so we're not costing so much energy and electricity for us. So it's a much better system.
Okay, then just to summarise then, transformers, it's based around efficiency and making a more efficient system. The step-up transformer increases the potential difference of the electricity. Remember, we're trying to keep the power the same, so if you increase the potential difference, therefore you need to reduce the current. This means less energy is lost and dissipated to the surroundings through heating of the electrical cables. A step-down transformer is needed to reduce the potential difference to a safe amount, around 230 to 240 volts, and in stepping down the voltage, you then increase the current. Okay, what I'd like you to do is identify the numbers representing the parts of the national grid and name the parts. So just write the numbers 1 to 5 in your books and just be ready to name each part. Okay, let's have a look at some of our answers. Okay, let's have a look at some of these labels then. So we've got the power station, we've got a step-up transformer, we've got cables, and then we've got a step-down transformer into our homes. Okay, so next question. Can you record 3 bullet points that explain how transformers work and why they are used? And you've got 1 minute to complete that question. Okay, let's have a look at a possible answer that you may have recorded. So, bullet point 1, a step-up transformer increases the potential difference, which therefore decreases the current. This results in less heating of the wires and therefore less energy dissipation to the surroundings through heating. And final bullet point, the potential difference is then reduced by a step-down transformers near our homes in order to make it safe to use. So let's have a look at some past exam questions on transformers and the national grid. So here, the transformer is 100% efficient. Calculate the output current for the transformer shown. So you've got 2 minutes to complete this question. You may need to use the equation that we've talked about. Power equals voltage times current. And just bear in mind it's 100% efficient, so the power going in should equal the power going out. And you've got 2 minutes to complete that question. Okay, let's have a look at the mark scheme for that question. Okay, so we've got 18 times 2 will equal your power, which must equal the same as 12 multiplied by the current, which leaves 3 amps. Okay, next question. A student makes 3 simple transformers, J, K and L. Figure 2 shows how the potential difference across the secondary coil of each transformer varies as the potential difference across the primary coil of each transformer is changed. Now you're going to use J, K and L on the graph, and the question is, how can you tell that transformer J is a step down transformer? And that's just worth 1 mark, therefore you've got 60 seconds to complete it. Okay, let's have a look at the mark scheme. Okay, so the question is, how can you tell that transformer J is a step down transformer? And it's worth 1 mark. So if you look at L, K and J, we can see along the bottom axes we've got our primary coil, and on the y-axis we've got our secondary coil. So for L, we can see there's 6 volts in the primary and 12 volts in the secondary, and that would imply that L is a step-up transformer. If we look at K, we can see that we've got 6 volts in the primary coil, and we've got 8 volts in the secondary coil. Once again, it's a step-up transformer. The voltage is increasing from the primary to the secondary coil. And then finally, J. So we can see that there's 6 volts in the primary coil and only 4 volts in the secondary coil. Therefore, there's less voltage in the secondary coil, which would mean that J is a step down transformer. And there's the answer. The potential difference across the secondary coil is smaller than the potential difference across the primary coil. Okay, so final question. Why is electrical energy transmitted at very high potential differences? And that's worth 1 mark. Therefore, you've got 60 seconds to complete it. Okay, let's see what we've got as an answer. Essentially, this is all about efficiency. So, why is electrical energy transmitted at very high potential differences? This would mean that you have a reduced current, which means less heat, energy, power being wasted in the power lines. So it's all about efficiency of the national grid system, and that's worth 1 mark. So that just remains for me to say thank you very much for listening to a basic introduction to the national grid. Thank you.